Hey everybody, welcome back. Good to see you again. Mr. Smith here. In our first slide deck on thermodynamics, we briefly touched on the fact that solids, liquids, and gases all undergo some kind of thermal motion because they have kinetic energy. But gases, because they have weak intermolecular forces, are free to bounce around, and they obey entirely different properties than solids do. So what we're going to do is give you a quick reminder here about some gas law ideas, and we're going to play with an app along the way. So first, ground rules. Ideal gases follow the rules that you see on this slide. The understanding is that when they collide with the walls of a container, they never lose energy. That's what perfectly elastic means. They don't attract each other at all. That's the second assumption. The third thing is that when they collide with each other, nothing happens. There's no loss of internal energy. So particles can give energy, but the loss and gain of energy is always equal one to another. Okay? So given those assumptions, let's go play on the PhET website, and we'll illustrate a couple of the gas laws and hopefully bring it back to your mind. Okay, so once we launch that PhET app, what we see is that we have a choice of options. We're going to launch the ideal gas model. And you can see I've got an empty box where I have no gas molecules exerting no pressure at no temperature, and we've got to add some gas. So let's go ahead and pump our bicycle pump. Let's throw a few molecules in there and see what happens. Let's throw a few more because we want this to be a little more exciting. Okay, so now we've got molecules inside of our closed container, and we're reading some temperature. So 300 Kelvin, a little bit warmer than room temperature most days, okay? So what we want to do, let's hold the temperature constant for this first simulation. What do you think is going to happen if I pull this lever that direction, pull it to the left? I'm going to make the container bigger, and the pressure is going to change, right? Right. Bigger container, smaller pressure. And so what we have there is the first of the named gas laws, that there's an inverse relationship between the volume of gas and the pressure that it exerts, as long as temperature is held constant. So P1 V1 equals P2 V2. Don't sweat about writing down the formulas. We have one slide with all the formulas you're going to need to one place. Just wanted to remind you, Boyle's law has to do with pressure and volume being inverse with one another. So let's go back to our sim and see if we can discover another one of the named gas laws. So in this simulation, what I want to do is go ahead and keep the pressure constant and play with another variable. Let's add a little heat to that and see if my common sense turns out to be true. Oh my goodness, it's as though when I add heat, in order to keep the pressure constant, the container has to expand. So there's now a relationship between volume and temperature of the gas. Yep, there you go. So if you guessed Charles' law for that last example, congratulations for you. You still don't have to write down the formula just yet, but what it says is that there's a linear relationship between the volume of a gas and its temperature. But the temperature is a kind of a special concept here. As scientists got better in the 18 to middle 1800s, they got better at cooling gases down. And the linear relationship that you see here clearly pointed to some distant temperature at which gases volume would literally go to zero because the gases stopped exerting pressure altogether. And they called this temperature absolute zero. So a couple interesting things. We now know that 0 degrees Celsius is 273 Kelvin. So this absolute zero temperature of Kelvin scale does sync up with our Celsius scale. The other thing was that gases turned out not to be ideal. So that as oxygen, for example, was the first one, 1877, oxygen right around here collapsed. And the attraction for oxygen molecules for each other turned out to be strong enough that they all glommed together and formed a liquid and became like maple syrup if you just got them cold enough. So a couple fun facts. What we're going to do right now is unleash all of the formulas and take a minute, pause, write them down, and then we'll talk about them. Okay, so here we go. All right, so I assume that you paused, or if you didn't pause, then you're ready to listen anyway. This gas law, combined gas law, it's really all of the gas laws mashed together. So story is that Charles, Gay-Lussac's, Boyle's law, Avogadro's law, they're all in here. The bottom line is that when you're taking a gas from one state to another state, this is your buddy. You don't have to use variables if they're not mentioned in the problem. You can just cross them out and invent gas laws as you need them. So you really only need this one. The second thing is, if you're trying to dial in one state of a gas and learn how pressure, volume, number of moles, or absolute temperature connect, then this is your friend. I expect that you guys have used all of these, the first two, just fine. One important note, there are two units for R. There's a physics unit and there's a chemistry unit. Their labels are not the same, so it's important to pay attention to labels, and we'll get into that. Thirdly, I think there's a formula that you may not have seen. So PV equals nRT, N stands for the number of moles. In PV equals big N KT, big N stands for the number of molecules. So as we've seen this whole school year, there's like a bulk there's a bulk formula that deals with matter at the aggregate scale. And then oftentimes there's a very small unit, kind of like joules and electron volts would be units that go with the bulk scale and the very tiny scale of the world. So PV equals NKT has a different constant. What I think might be fun would be to see if you could divide this number right here by that number right there. So divide R by K. Let me know what you get and bring it up in class, okay? Finally, on this slide, stuff that you should know. Here are conversion factors between common labels. You probably know about these. Gauge pressure is a thing we will actually talk about in just a second. So anyway, use these, write them down, and we'll get busy with them right now. Okay, so you see one of my all-time favorite cyclists, Greg LeMond, and typical huge lung volume on a professional cyclist. What they ask us is how many molecules could this guy hold in his lungs at standard temperature and pressure. Okay, so I know right away that this is going to be a PV equals nRT problem. And I know that that's the case because they don't take the gas from one state to another state. They're just drilling into a single state and asking us about it. Okay, so what I'm going to do first of all is just be sensitive to labels. When I see 6 liters, I'm thinking of using the R that we usually use in chemistry. It's 0.082 atmosphere liters per mole degree Kelvin. And when they tell us standard temperature and pressure, then I'm free to pick the units of pressure that make it easy. So what I'll do is solve this thing for N and then set it up, and we'll get busy and talk about it. So PV over RT gives me N. Let's go write down those units. I'll plug it in, and then I'll come right back to it with you. Okay, so as you see, we chose the right units for pressure that are compatible, standard temperature, all that works out. And what we get here is N equals 0.27 moles of the gas. Okay, so what you're going to see me do is just go ahead and convert that to molecules, which we've done here. Easy enough, 1.6 times 10 to the 23rd. There you go. All right, in the next example, what we're going to do is spring a little bit of a new concept on you. Gauge pressure is a pretty simple concept to explain. If you were to take an absolutely flat tire and snap a tire gauge onto it, that tire gauge will read 0 psi. And yet, you should know, it should make sense, that the tire actually has 1 atmosphere of pressure in it. So the way it works is that the gas law pressure, that we'll call P, is always going to equal the gauge pressure plus 1 atmosphere, because you don't want your tire gauge to read 1 atmosphere when the tire is dead flat. Okay, so that's just a little bit of reality. What I'll do is just then adapt the info they gave me here. 32 psi plus 1 atmosphere, 14.7 psi, gives me the actual pressure I'm going to want to write down, which is 46.7 on the psi scale. Okay, so now that we've done that, we can get to the actual physics problem and use that. So what I see here is definitely a combined gas law. I'm taking the gas from one state to another state. So what I'm going to do is actually only write down the part of the gas law that I see operating. And if you cared, this was a thing called Gay-Lussac's law. What I'm going to do is to solve this thing for the second pressure. So P1 over T1 all times T2. And what that looks like is 46.7 psi. Was our original pressure. It really does matter that you get those temperatures in kelvins. This will not work at all if you don't. So this is 293 kelvins. Kelvins are the only temperature scale that really means anything in the actual universe. So 268 kelvins is our -5 degrees, our second temperature. And what I get there is 42.7 psi. So you might think you're done. You're almost done. That's the not the gauge pressure, that's the actual pressure. If they say, hey buddy, I want the gauge pressure, what you have to do is reverse the process you just did. So I subtract 14.7 and I end up with the answer that I was after. So my 32 psi tire at this temperature turns into a 28 psi tire at that temperature. Okay, so example number 2. Example number 3, don't try this on your own. You'll just waste a lot of time. So here's the thing about this example. When I see 5 meters cubed, it immediately makes me think about the units that I'm going to choose for R. We're not taking a gas from one state to another. This is like our first example, our bicyclist example, and then I'm going to use PV equals nRT to solve. So I know I'm going to end up dealing with R. So what I'm going to do here is just read a little further and then make some choices. How many kilograms of air? That's going to definitely relate in some way to the number of moles. So just like the first example, I'm going to isolate PV over RT to solve for N. Here's the thing though, that I know that I have a choice for R, 8.315 or 0.082 atmosphere liters per mole degree Kelvin. I'm going to show you how the 8.315 works. Remember that 8.315 has the labels of joules per mole Kelvin. And I also want you to remember that a joule from work equals force times distance is equal to a newtons times meter. Okay, so in the next slide, I'll show you how this all breaks down in a way that will be useful to you going forward. So a Pascal is a unit of pressure that's equal to newtons per meter squared. A volume of cubic meters, as I have here, 5 cubic meters, if I took this pressure and this volume and multiplied them, hopefully you can see how it would end up with newtons times meters to make that joule unit that I was talking about. So bottom line, when I see 5 cubic meters, I often think that they're steering me in the problem towards 8.315 for my R. So what you'll see me do in this example is just do a little bit of converting. So pressure, they give us is 60 psi. And what I'm going to do is do a little converting here to get over towards pascals. So I know that atmospheric pressure is 101.3 kPas, kilopascals, and that's equal to 14.7 psi's. So I convert the pressure unit, and what that ends up being is 514.8 kilopascals for my unit of pressure. And then everything else I think is pretty straightforward and good to go. So what I'll do is I'll just go ahead and rewrite my N equals PV over RT. And let's go ahead and I'll pause the slide deck, pencil in the choices that I made, and you can see how that happens. Okay, so you can see what I've done here. I'm sticking with the 5 cubic meters. I've converted to kPas. When I plug this into my calculator, I'm just going to have to remember that this really is thousands of pascals, and I've made the change to Kelvin temperature. So when I go and plug all this in, I go ahead and get 157 moles of the gas. Okay, so in the next slide, we'll just put this thing to bed. So I've got 1057 moles for the amount of the gas. When they ask me how many kilograms of air the tire contains, I'm now going from moles to grams or moles to kilograms. Check it out now. What I have to do is actually remember that nitrogen is diatomic. So if I need to get into mass units, the molar mass of N is 14 grams per mole. The molar mass of N2 is 14 grams of N2 per 1 mole. Okay, so that's a little thing, but you do want to watch out for it. So it'll double your mass sometimes. And then we're just going to go ahead and convert this thing to 1 kilogram over 1,000 grams. And long story short, it turns out to be not a small number. This is like 29.6 kilograms of nitrogen inside that gigantic truck tire. So it really does have weight. Anyway, that's a lot. We're going to practice with this in class. Bring questions if you have them. Great to see you. Take care. Bye-bye.